Hi, so I'm Rafi Vivanti. I'm from Refael, and today's talk is about towards self-learning, self-driving vehicle, reinforcement learning system for autonomous driving. So, if anyone is not aware, what is reinforcement learning? It's learning from a self-experience. So we have a machine learning agent in the world or in the environment. The world gives the agent a state, S. The agent takes an action A, and the world or the environment gives back a reward. And we want to make an algorithm to maximize this reward. So reinforcement learning can learn even if the game rules are still unknown, if the rewards are delayed and even sparse, if there is no supervision, but this self-supervision. And even if the action make an impact on the environment itself. In recent years, many achievements of reinforcement learning, superhuman performance in many games like Atari, chess, some control problems, and I guess you heard about it. So our mission today is to teach a vehicle to drive in a specific off-road area. Please note that we will train and test the vehicle in the same place. So we only learn how to drive in one area, one off-road area. Now we don't want to use supervised learning because it would require a large annotated databases, which we don't have. And we can't do reinforcement learning with a real vehicle because we need many iterations it's too slow and very unsafe. So our solution is to copy-paste the environment into the computer, and we do that by realistic modeling the area from aerial images only. And then we will train the reinforcement learning algorithm inside the model, inside the computer. And as a bonus, if we succeed to do that, we can learn how to drive in unapproachable area like other planets only from aerial images of it. The challenge. Our main insight in this project is that driving involves two different tasks, navigation and obstacle avoidance. They both affect the location and orientation of the vehicle. However, they are very different. Navigation or path planning is a strategical task. It has path rewards. I mean, if you only get a reward when you reach to the target. And it has a geometrical input with the coordinate of the target. On the other hand, obstacle avoidance is a tactical task. It has dense reward. In each step, you know if you crashed into an obstacle or not. And input is usually visual, a depth map or a obstacle map, or only an image like humans are driving. And we found that doing both together is very hard, so we split. So we have two systems. The navigation, the path planning, is happening before the mission. Its input is the target location and the current location. It uses the 3D model geometry, and it produces as an output a track. The interesting part, the reinforcement learning part, is the obstacle avoidance system. This happens during the mission. At each iteration, the 3D model is rendered to the current location. The reinforcement learning agent takes this image and decides on an action. A driving decision. This, of course, puts him in another place, and we have to render the image again. And we can get a crash reward from the 3D model. So let's focus first on the navigation system. How do we do it? So we start with the 3D model, and we extract the 3D geometry from it. Then we do segmentation by possibility. And then we use watershed segmentation on the distance from obstacles map to get the trails. And you can see color-coded. I don't know if you can see it. The width of each trail is color-coded in this map. Next, we use the platform real width to remove narrow trails. And we use the Dijkstra algorithm to find the shortest path within those trails. So now we have a path to the target, but this is not enough. We want to summarize it into a list of waypoints. So this is the output is like Waze. It tells you in 100 meters you should turn left in that degrees. The reinforcement learning part, the avoidance system, this happens, like we said, during the mission. In each driving step, the model is rendered to the agent location. And the agent pose is such that the next waypoint is always in front of it. This is the way we tell the avoidance system about the navigation system decision. The agent uses the rendered image to avoid obstacles, while unknowingly progress toward the target, because we always put it in a pose such that it will progress toward the target. Now we wrap the driving simulator with a game with scores, and we train the reinforcement learning agent to maximize the scores. We compared 3 state-of-the-art actor-critic-based reinforcement learning algorithms. They are called PPO, A2C, and actor. The reinforcement learning agent is modeled in a convolutional network. Its input is a rendered image, like we said. Its output is a driving decision, straight, left or right. We share the convolutional layers between the actor and the critic. So the convolutional layers output is an image representation, and the actor and the critic, which are both one fully connected layer, are using it each for their purposes. And some other details. We use the random tracks. Each game starts from a different location and ends in a different location. So our agent will know how to drive in all the trails of the model. We introduced random obstacles, like you can see with the yellow arrows. It's like if you get up in the morning and get out of your house, it's the same street, but different cars are parking different places. So our model, our agent in each game, he sees different obstacles within the same 3D model. And we use multiprocess. We train it parallel on many games, but only one training agent makes all the decisions. Okay, some results. So in a cyan line, you can see the human mean performance. We measured it on 2 gamers playing for 1 hour. As you can see, they did very badly. One of them was me. And it's because this is a very hard game, because I don't know how to program a good game, an interesting game, or a possible game. So you can see that both the A2C and the PPO algorithm reach superhuman performance very quickly, within 1,000 games. And then they proceeded to do much better. You can also see that the actor algorithm did not converge at all. If we smooth the graph a little, we can see that although the PPO algorithm is indeed monotonic, like it's designed to be, the A2C algorithm, which is volatile and sometimes retreats from its very good progress, however, it converges in about half the time, and to a much better result. So here we can see the agent riding inside the model. You can see it maneuver to avoid crashing into obstacles. If you see sometimes that it's doing a very sharp turn, like now, it's because it reached a waypoint and it's going to the next waypoint, which is in a different direction. And I think that's it.
Thank you.
Okay, no, that's it, the movie. So our method has several limitations. So we did not address at all moving obstacles, like moving cars or other vehicles. We also assumed an open area, off-road. We did not address traffic rules. We did not address steering car. So like we said, the way we tell the avoidance system about the navigation output is that we steer the vehicle towards the next waypoint, while it should be able to move in another direction. So you can imagine a drone doing that it looks at one point and moves in another direction. A car cannot do it, so we still can't control a steering car. Another point is blocking obstacles. I said we add the obstacles, but it's never blocking the roads. If the obstacle is blocking the whole passage, we need to reconsider the whole navigation. This is also the problem if we miss the turn and enter to the wrong trail. So our system cannot do a U-turn. So if the navigation is gone, it will crash sometime. It will not reach the target. Future work. So of course we will address all the limitations. Another interesting thing we plan to do is we want to use a GAN algorithm for even more realistic images. So I think the images are pretty realistic, but they are not similar to what the robot will see, the vehicle will see when it's in the real area. And you can see in the image in the top that it looks a bit different, even if no other interference, like the sky is white and not blue, and so on. And we want to make it, we want the vehicle, when it will drive in the area, to see exactly what it saw in the 3D model. We also want to introduce some interference like rain, darkness, fog, dust, and mud. You can see here in the middle image that it's the same place where we trained the model, but a little rain made the ground in a different color because of the mud. And you can see in the lower image a little pool. All those things we don't want the robot, the vehicle to, don't want it to surprise him. So we want to train, we want to make images from the model, realistic images with all those interference, and train the vehicle with it. We also want to introduce control learning, which means to copy-paste the vehicle behavior. So a vehicle has all kinds of control restrictions, like delay between the command and when the command is committed. If you control the vehicle using a steering wheel and you steer with one angle, so you want the car is doing something else. It's not doing what you tell her. So we want to model all that. We want to use deep learning to do that. We want to drive with the real platform and to copy-paste its behavior into the computer, and then train the reinforcement learning with those restrictions. This is the control learning. And finally, we want to take all this together and to drive a real platform in the real area, which we modeled using the 3D model. And we want to test inside the model area. You can notice that we chose a training facility, a military training facility, which we can make sure no one will be there when we will train our vehicle. Thank you very much.